Hello everyone, I am Sampath Koti and I am here to present our federated scan, leveraging server client alignment for unsupervised source-free domain adaptation, published at Back 2026 from VCL Lab at ISC Bangalore. So this is the basic framework. The server broadcasts its current aggregated model to all the clients. Each client but then uses the server model along with its own local model that it has saved from its previous rounds to compute the SCAl alignment loss. It also runs pseudo level estimation using prototypes and computes the LOA loss. Both losses are combined and minimized over several local gradient steps. The updated client weights are sent back to the server, which are aggregated then, and the cycle repeats. Notice the two augmentation pipelines. One is a weak augmentation pipeline, where each sample goes to random crop, horizontal flip, which preserves the semantic content, gives server model and the client model input to produce reliable pseudo labels. Strong augmentation, on the other hand, randomly picks two of these transformations from this list and applies it to the input sample to generate diverse and perturbed view that forces the client model to learn representation that are robust across domain variations. Coming to the SCAl loss and the entire objective. The SCAl loss has two different parts, LKL and LKG. The K here refers to the kth client. So the client alignment on LKL computes the K divergence between the client's own weak augmentation pseudo labels and its strong augmentation soft predictions. This enforces self-consistency. The client representations should be robust, strong visual perturbations. Whereas the server alignment terms, LKG, computes the KL divergence between the server model's weak augmentation labels and the client's strong augmentation predictions. It pulls the client's representation towards the global server's understanding of the world, countering the drift that the local adaptation otherwise would have caused. A confidence gate ensures only predictions above threshold tau contribute, and additional hyperparameters lambda L and lambda G balance out these two terms. Finally, the SCAl and the LOA loss are combined that together forms the local training objective for the model. Another practical challenge remains the confidence threshold tau. A fixed threshold is brittle. So if we set it too low early in the training, you flood alignment with noisy labels. And if you set it too high and you end up filtering out too many samples, so you don't have anything to train on. And additionally, different clients with different domain gaps need different thresholds at different point of training. Our solution proposes an adaptive tau based on the skewness of each client's per sample entropy distribution. We compute Pearson's skewness, gamma, variation. This does not require any additional model passes. As you can see, there are three main ways this is applied. When the gamma is negative, the entropy distribution is heavy on the higher end. The model is uncertain. It relaxes the tau to let more samples contribute. When the gamma is near zero, the entropy is balanced. The tau is kept the same. When the gamma is positive, the model is confident and making good predictions. We tighten the tau to keep the cleanest pseudo labels, thus updating the tau every round for each client. So here I am presenting the results on Office as 4 major domains with 65 categories in each domain. We can see our proposed method, FedSCAl, performs well across all clients. And we see on an average improvement of 3.5% on art source and 2.8% on clip art, 3.6 on product and 3.5 on real world source. Coming to domain net small dataset, this is a much difficult and much tougher benchmark with 6 domains. Here you can see our proposed SCAl model performs shows an improvement of 12.4% over the second best thing, which is FedMode. And additionally, it shows similar improvements across all the source target settings, where our model performs much better in comparison to all the other baselines and other benchmarks that we are considering here. So natural question comes next. Why does SCAl work? Is it genuinely improving pseudo labels that drive local adaptation, or is it just acting as a generic regularizer? We demonstrate this to two findings. First, the delta accuracy is always positive. For each client in every round, SCAl produces better pseudo labels than the non-alignment baselines. Second, the gains are compounded. Better pseudo labels in round R produces better adapting, which generates even better pseudo labels in round R plus 1. The server alignment creates a cycle of self-improvement. Next, I present a ablation study where, as there are two parts in our SCAl objective. One is the local alignment loss, the client alignment loss, and the server alignment loss. If you remove both, it's basically Fed LOA. And you can see if you remove even one, the accuracy goes down, and showing that both the losses, both the components of the SCAl are essential and help in improving the alignment and curbing the client drift. Additionally, we show the importance of the adaptive threshold. We see that adaptive threshold improves on the performance on the addition on top of the SCAl loss. Finally, what happens when we change the objective, the base LOA objective, to other than short? Here we show for two other methods, BMD and Yocon, and we show that in both of the cases, our proposed method, FedSCAl, outperforms the Fed LOA. So, FedSCAl tackles a hard FEDA problem where there is no source data available. Additionally, the clients that are participating in the federation have unlabeled data with extreme interclient domain gaps, not to mention the domain gap between the server and each client. The proposed SCAl method aligns client and server predictions using weak strong augmentation pair, consistently improving server label quality, reducing the client drift across all benchmarks. And finally, the adaptive threshold dynamically adjusts the tau via entropy skewness. This happens per client and per round, removing the need for fixed threshold, improving the overall performance of the proposed method. Finally, we show state-of-the-art results on 3 of the datasets, Office Home, DomainNet, and Office 31, outperforming all the competing benchmarks and baselines across all domain settings.